Good afternoon, everyone, and welcome to the DARS talk series hosted as a part of our the fall 2025 ARC 3 of 5603 3 a.m. studio, augmented adaptive additive manufacturing and architecture here at the HCoA at the Texas Tech University. Today, we are privileged to host Ana Anton, architect, researcher, and co-founder of Anton Reiter. Her work sits at the intersection of additive manufacturing, material innovation, and architectural design with a particular focus on large-scale 3D printed concrete. Notably, her involvement in projects such as Torah Alva illustrates how additive construction can address questions of form, modularity, and assembly, logistics, and freeform structures. She holds a Doctorate of Science from ETH Zurich and a Master of Science from TU Delft. Her projects have been exhibited internationally at venues such as the Center Pompidou in Paris, Dubai Design Week, the World Economic Forum in Davos, the Design Museum in Zurich, and the Form Next in Frankfurt. In 2025, she co-founded Anton Reiter, a Luxembourg-based company that develops consulting and R&D solutions for building materials, manufacturing processes, and additive workflows. Please join me in welcoming Ana.
Hello, everybody. Thank you, Mark, for the nice introduction. And do you hear me? Is all good?
Yes.
Okay. And thank you very much, Sina, for the invitation to present my work. It is actually a very interesting moment in my career because I make the shift from research into practice, and this comes with many challenges, but also great opportunities. So just a bit of context about myself. For the past roughly 8 years, I was working at ETH, strictly focusing on 3D concrete printing. This is the topic I pursued in my doctoral studies. And then I applied this research at larger scale in the Toralva project, which was a large-scale demonstrator, actually more than a demonstrator, like a real project, in which these new technologies were applied in a real construction context. That was part of my postdoctoral research at ETH Zurich. This part concluded at the beginning of this year when I decided to move from academia into practice. First of all, because my research has reached a pretty advanced, mature point in which many of the ideas I developed can be applied into construction. And now I look at opportunities and possibilities of how to apply these things into construction. Let's go into the slides. So I want to briefly introduce the company and what we do, and then I will showcase some projects that I did in research. As I was mentioning, I founded a company, Anton Reiter, which is a technology company in which we want to develop products through either consultancy or joint ventures. So it is always about collaboration. Our mission in construction is to use as little material as possible to reduce material consumption, but through the use of novel technologies, through the use of automation, either of processes or of workflows, whatever brings efficiency to the construction process. So our company is not per se a startup, but it offers consulting services. and the research and development in several larger fields of construction, like building materials, manufacturing processes, specifically additive manufacturing, and digitalization of workflows. And from the main topics that we focus on is concrete technology in organic building materials, so not only concrete, but also design to fabrication workflows, which is more related to the
Yeah, Anna,
design process. And it is, yes,
not to interrupt you, but we're going to try to fix the audio a little bit on our end.
is it not?
It's just we're okay.
Is it better now? Okay, cool. Then I continue. Um, um, the company has two co-founders, myself and Lex Reiter. We both bring different type of expertise, and we shared our knowledge to build this company together on our main strengths. So first of all, design to fabrication workflows, which comes from my track of specialization. I am trained as an architect, and then I worked extensively in research on design to fabrication workflows. Lexi's background is in civil engineering and material sciences, particularly mineral building materials. And in terms of expertise, the achievements that we bring to the company are first and foremost on materials and processes. Lex worked on a large array of digital fabrication processes, but also material formulations. This includes slip forming, layered extrusion, but also mineral foams and geopolymers. From this expertise, it is looking at the fabrication process, but also at how to fine-tune the materials so that they are compatible with the process itself. And here you can see a diagram of possible fabrication processes that involve different materials in different forms. So we have extrusion processes of concrete that, depending on how things are implemented, they can be transformed from 3D concrete printing to digital casting, shotcreting, and slip forming. But the technologies can be implemented in a rather similar way for particle bed printing, either using selective binder activation or selective paste intrusion. Here it's an interplay between how the material is deposited, but also what materials are combined, how fast they harden, how they can keep their shape, either by being supported in this floating bed of particles or by hardening very fast in 3D concrete printing, layered extrusion. And if we talk about concrete and construction, I think reinforcement is a very important aspect. We also integrate strategies of how to add reinforcement that is compatible with the process. In this case, we have more experience in layered extrusion. We started our collaboration already in research in the National Center of Competence in Research Digital Fabrication, which is a large research program that developed at ETH Zurich for the past 10 years, I would say. It has in total 12 years and it is divided in 3 phases. The idea here is to put together different expertises, different research fields, and address problems that are bigger than one research field in itself. So that was the case of layered extrusion 3D concrete printing, where we, from the beginning, started with the idea to develop a process that makes sense for construction. And we had input from different disciplines at the very beginning of the process. So that allowed us to design what we want to produce instead of working with a process that already exists or trying to adapt it or fine-tuning it for fulfilling a certain task. The process we developed looks roughly like this. It is a robot that is able to deposit material. The system is controlled again through another computational interface, the Compass framework, which is a software package developed, again, part of the NCCR digital fabrication, but in this case from a different research stream, different collaborations. But you see how things come together and are applied modular in different types of processes. In the case of concrete printing, we used the same software as to control the robot as it was developed in this Compass framework. The system works with two material component, meaning that actually it's three materials, because we have the base material, we have the accelerator and the thickener, which are intermixed in the printing tool. And these two materials allow two types of control over the filament that is extruded. First of all, the hardening rate, so the vertical buildup, and the thickener would control how stiff the filament is, or the initial yield stress of the filament. This is all describing the materials and processes. Now we developed a process that we also applied it in construction. And as I said earlier, it was important to design a process that makes sense for architecture. In our case, what makes sense is to have a high-resolution 3D printing that is able to produce structures in a very controlled way. We wanted to have structural integrity of the parts that we produced, so we are able to optimize the shape for certain structural cases, but also use the minimum material possible. So here you maybe see these ducts that host the reinforcement in a rather complex shape. But the idea is to put concrete around the reinforcement in such a way that you use the minimum amount of reinforcement, but also the minimum amount of concrete. And then we also looked at the tectonic system, which is based on modularity, customization, and fast assembly on site. This is important because in 3D printing with concrete is very, or it's easier to print in controlled environments and have a piece that is designed with a more complex geometry that can be printed in different orientations and assembled later on. That is part of thinking about the tectonic system of how we develop different components that come together into real buildings. These tectonic systems were applied in real scale projects, also in a research context. This part now will showcase my work at ETH Zurich. And I have selected 3 projects that also link to how I see the activities of the company, how to develop design to fabrication workflows for different fabrication processes, having in mind that the system has to be modular, easy to assemble on site, reduce material. I will start with the Nubian slab, which is a fabrication system that relies on the ancient technique of Nubian vaults. We got our inspiration from those geometries because we could control the material in such a way that it could hold its shape only by the friction to the previous layers. So we actually put the layers of materials deposited in midair to replicate the bricks into a Nubian vault. So you can see that we can achieve this printing in midair almost only by creating funicular geometries that are stable during printing. The idea was to use this technique to cover the floor of an extension in an existing house. And you can see here that we are talking about roughly 16 square meters, but a non-standard perimeter. And our idea was to use components that are unique but follow the same principles, the same overarching logic, to create a prefabrication system in which these elements are simply transported on site. So they are prefabricated, they are transported on site, put into place, and then we could add reinforcement and cast regular concrete. This is, in my opinion, a very good example of where digital technologies make sense to be applied in construction, especially in refurbishment projects, because they come already with a custom context. So if you find a perimeter that is a bit jagged, and then you can create perfect components that fit, I think it makes sense to talk about customization in construction. With this simple project, in a way, we also proved that we can reduce the use of concrete. Having these vaults enabled us to reduce the material by 20%. And this value could even increase if we talk about larger spans and thicker slabs that have larger structural depth. This is all about the Nubian slab. Next I will briefly introduce Tor Alva, which is again an amazing opportunity to showcase the interdisciplinary research of ETH Zurich in a very creative context. So Tor Alva is a project we developed for a real client, the Origin Foundation, which is a cultural foundation. It was designed by Michael Hansmeyer and Benjamin Dillenburger on the architectural part. And the scope of the project itself is twofold. First of all, the client wanted to create an inspirational space for the performing arts, which is the activity of the foundation. Through their cultural activities, they want to revive the rural villages in the Graubünden region and attract different kind of activities and different kind of people to the region. And the other aspect that we wanted to demonstrate was how to apply in real construction the research that we developed for so many years at ETH. And in this context, I think concrete 3D printing was chosen because it was one of the most mature processes that could have an application in construction. So we started with an initial design and a demonstrator. Back then, I didn't include a render of the previous design, but back then the project included a different building system that evolved after the demonstrator. So it was really useful to test the ideas at one-to-one scale and learn from the experience. So the building system relied on 3D printing of a formwork that would be reinforced with regular rebar cage and cast on site into modular components that are assembled through post-tensioning. So basically we have these columns that are hollow, partially cast between a hollow pipe and the 3D printed form. Each column has 4 post-tensioning rods. You can see them here on the top that post-tension the 2 slabs and the column together. What we have learned from the demonstrator was also detailing between was also that the detailing between 3D printed components is very important. We tried here to use between the segmented elements prefabricated concrete sleeves to account for the imperfections of the layer. However, this was not 100% successful, and we came up with a different strategy for the final tower. And you can still see that the process had imperfections by how the elements were printed. What we have also learned is that if we work with only vertical elements, of course, it is easier to produce them and to print them, but they also need many post-tensioning tendons or rods to connect them to the slabs. So we wanted to get rid of them and have less elements to assemble. So in the end, we moved towards a totally different building system. But to make space for the new tower, we had to dismantle this demonstrator. And among the creative activities of the foundation was that the columns were used to create a permanent bus stop in the same village, which nicely reuses the 3D printed columns and one of the slabs. And it also makes use of the functional integration inside the columns because when it rains, water is collected on the top and it's driven through the hollow core columns through this lower part to the draining system. I think it's an interesting exercise to make a temporary demonstrator more permanent and integrated into the existing fabric of the region. And with this image, I want to go to the final project demonstrator of Tor Alva, which you can see here in relation between the two. So after the demonstrator, we had a radical design change. We moved from vertical columns to branching columns because they take better lateral loads. Another decision was to move away from stay-in-place formwork to 3D printing columns directly with the printing material being structural. I don't know now which decision was stronger, to use the 3D printing material structurally, or that we couldn't produce branching columns like hollow elements and simply introduce reinforcement because of the geometry. So the decision here is a bit more complex, but these branching columns perform better in lateral loads, and you can also see that the building system changed from individual columns and slabs to elements that are structurally sound in themselves. They have these triangles, and they already contain part of the slab and part of the top floor already in them, and it's just a modular puzzle that easily gets assembled on site with self-similar components. Because we use the material as load-bearing, we had to do a structural testing campaign, again led by a group from ETH Zurich as an interdisciplinary research, the chair of concrete structures and bridge design. And we printed one-to-one scale prototypes of the V-shaped columns, and they were reinforced exactly how the columns would be. And we had two such specimens. One was post-tensioned, and the other one was without post-tensioning. The good finding in this case was that the column without post-tension also exhibited a ductile behavior. So for the construction of the tower, we were able to actually take out post-tensioning in many of the floors. The component looks something like this. It has a precast base, the 3D printed part, and the precast top. The column is reinforced with interlayer rebar and with vertical rebars that go from the base through the column to the top and have these voids that are grouted in such a way that the entire element becomes monolithic. Here you can also see the assembly points between components. These will be post-tension screws to hold everything together. The column consists of three main layers. The outer layer is treated as ornamented layer. It is not part of the structure. Only the inner two layers are part of the structure. The second one hosts the interlayer reinforcement, which is, in our case, stainless steel. Because we had worries about the durability in combination with the 3D printed material, and we operated on such a tight timeline that we didn't have time to see the long-term behavior and the corrosion rate of regular steel in 3D printed elements. So we opted for stainless steel reinforcement, and the innermost channels create a space for the main reinforcement, the vertical reinforcement, which is later on grouted to create the structurally stable component. You can also see that this way of working with procedural design offers nice opportunities to keep the force flow continuous within the column by self-intersecting the branches and solving the intersection in a simple way. We alternate the rebar rings in different planes to avoid the intersection, and we slightly shift the channels from one column to the other so that the rebars do not self-intersect, the vertical rebars do not self-intersect. In the end, we reached three types of components, levels 1 to level 3 columns. are 3D printed with passive reinforcement, so this interlayer reinforcement and the vertical reinforcement. Level 4 columns, which are really the tallest elements, because they are 6 meters tall, they cannot be transported on site in vertical position. So because they had to be flipped with this 2 crane system, they needed to have post tensioning for accounting for this transportation load case. Only these columns have both passive reinforcement and post tensioning. And then we have the elements in the cupola, which have no passive reinforcement. They are only post tensioned because they are also part of a compression dominant structure, the cupola. The elements were produced at ETH Zurich with the printing system that was developed, part of the NCCR digital fabrication, interdisciplinary research. We had to segment the components, the 3D printed part, to fit the printing space and to be able to transport the components later on. Unlike the previous project where we had this concrete precast in between the printed components, we opted for a process that replicates match casting. We 3D printed the last 5 layers of the component that comes on top. We put a thin plastic film between them, and we printed the component that comes on top. In the end, the joint can be very, very clean, almost invisible when you assemble these 2 components together. Another aspect of the research part was how to automate the placement of reinforcement. This was tackled into an Inno-Swiss with implementation partner research project, which had as partners the contractor for the constructor of the building and an ETH spin-off, Mesh again, that works with digital fabrication processes of rebar. What we did in this joint consortium was to develop a process in which we were able to print and place rebar in the same time without interrupting the printing process. This was tailored for the column typology of Tor Alva, and we had a process of alternating the positioning of rebar with the robot so that the printing robot will not collide. So let's say it's not a universal strategy of reinforcing concrete printing elements. It is still project specific. And to a certain extent, I think rebar integration will stay project specific and needs to be detailed as part of the fabrication process of the desired elements. So we produced many components, more than 200, from which we had to reprint only 4, which I think it's a great success given the tight schedule and the fact that we were producing the columns in a research environment. The precast bases were produced by an industry partner, also with the help of another ETH spin-off, Saeki this time, who produced the formwork for the non-standard geometry of the bases. You can also see that these precast elements accumulate all the functionalities of the column itself. It has to be heavily reinforced. It has ducts for electricity and light. It also has this interesting part of producing voids with the inclination of the columns that comes on top to make sure that the rebar, which in some cases is 6 meters long, can fit from the top to the bottom in a continuous piece. The prefabricated bases were delivered to the prefabrication hall together with the 3D printed components, and they were assembled one level at a time. And after one level was assembled, they would be taken on site and assembled on site. It took roughly 2 days to assemble a full column, and the process was parallelized for multiple columns. First, they would stack the elements, introduce the rebars, glue the segments together, wait for 24 hours for the glue to set, and then the thin grout could be added in the hollow channels to fill and bond the vertical reinforcement. As I mentioned, level 4 columns were the most difficult to assemble and to transport. But I also think that they are one of the more spectacular elements because they create the top part of the tower, the stage. And here you can see also the setting in which the tower was assembled and how the surrounding helps create an interesting atmosphere for this a bit non-standard shape. The tower was fully assembled last year, and the opening took place this year in May. The tower is positioned on top of an existing building, and the main entrance is done through this rather opaque space through an entirely closed concrete surface. And as one goes further up into the tower, the columns become thinner, and one can experience the surrounding beautiful alpine landscape. The functional room, which is the theater stage under the cupola, can host up to 50 people, and it is very porous and open towards the exterior. You can also see the cupola here and how a visitor could experience the space. You can also see that the columns are not perfect in the sense of a perfect printing process because the material still has a behavior of its own, and one needs to work with this variability when designing for concrete printing. This is the setting of the tower in the natural landscape, which I think fits very well with the surroundings, with the white houses, and how it projects on top of the green fields. I want to show the names of all the people involved in this amazing project. It was not only a research project for us, it was also an excellent way to work with the foundation, but also with the local industry partners to create this project in such a way that fulfills all Swiss building standards. So with the projects I showed today, I wanted to emphasize that the true potential of 3D concrete printing in construction does not necessarily lie in having these monolithic structures that are printed on site. But it's rather into creating more special high impact components that can enable new building systems, more agile, more modular, easy to assemble and disassemble, that have more special functional integration and that adapts to complex site conditions. I think that this is very important for new technologies in general. And we should also think of all these implications in construction when we work with new technologies. And instead of a conclusion, I actually prepared a set of questions that are framed in the context of 3D concrete printing, but I think that they are applicable to any new technology in general. So sure, what types of construction projects does 3D concrete printing provide the most value? So we need to think of is this new technology bringing something new compared to traditional methods? Or are there existing methods that are more practical, more economical, more easy to implement? Then we should also think if 3D concrete printing is inherently more sustainable, or the value it brings to the table really depends on how we use it. And beyond novelty, because we tend to be really fascinated about how novel projects can create new shapes. What is the tangible and lasting impact of these technologies in the construction process? What are the costs, the sustainability implications, and the labor dynamics? And the last question that I want to reflect on is how does 3D concrete printing challenge the assumptions of conventional design, engineering, and building standards? In the projects I have shown, I always explored this interdisciplinary collaboration, and I think they were enabled by interdisciplinary collaboration. This is an important lesson I learned in research and I want to take now into practice. Thank you for your attention. I think this is all from my side.
Thank you, Anna, for an inspiring and thought-provoking lecture. I was impressed throughout, and I'm glad to be incited by the presentation. To start our Q&A, I was wondering if, considering the first set of vaults, the Nubian vaults, if there was any sort of like non-planar considerations when proposing Torah Alba.
Yes, we actually started to print some of the columns with non-planar layers. But in the case of Toralva, we also had to be pragmatic and take decisions to simplify the building process in such a way that we could actually build the tower. Of course, it would have been better from a structural point of view to have the layers perpendicular on the branch, as you would expect in having branching columns, and that could be done. We tested the printing of such layers, and it worked. However, we were very worried about the assembly process. It is way easier to stack the elements under gravity, and when you have so many elements to assemble and a very short timeline, the pragmatic decision was to print them with horizontal layers.
Yeah, that makes sense. I think the pragmatism often takes over when trying to realize these projects.
Yeah.
Do we have any other questions on the floor?
I'm curious how far for the, I think
You want to come up here and ask? Or really projected ones?
for the Dudian form, like the print that you were showing us at the start, how far have you pushed that on like its horizontal span?
The horizontal span. It is a rather complex equation to figure out the material you are printing with, the initial stiffness, the thickness of the layers, how much surface of contact they have between them, how long the print path is. And in our case, if I can go back to the slide, we were struggling a bit with the print path length and the opening of the vaults. Because of the house being a refurbishment, we didn't have enough space to really create deep vaults. Taller vaults would have been better and easier to print. So this is why actually the elements have two integrated vaults, one after the other, so that we can have a long enough contour for the material to harden and to be self-supporting. However, these images that I'm showing here, it is with an improved process, and we could control the material to such an extent that we could have only one vault and a very short print path.
Cool, thank you.
I think that'll be all from us. On behalf of the studio and Texas Tech University, I really appreciate you presenting to us today, Ana. Thank you.
Thank you. Thank you for